Now we are going to revisit an old problem and look for a solution to it. So the old problem was that we have Alice and Bob exchanging messages, and they have a common key that they have established, maybe offsite when they meet in person or something. But then there's this other person, Eve, who is trying to actively intercept their message and break it, right? So then, but right now, and so Eve really seeks the key without actually confronting Alice and Bob. And then once Eve has the key, then she completely understands their messages, or, with a little bit of time and energy. So maybe a different solution is to say, okay, well, instead of having this, so we still have the three people involved and we have this key, right? And so instead, what we want to try is to say, well, maybe Alice has her own, still has a key, but what she has said now is she's taken the communication between Bob and herself out of the equation and just said, well, if you want to communicate with me, you have to leave me a message in a lockbox. So here's my lovely little box, and if you think about it like an election box or a ballot box or something, Alice is the only one with the key to the ballot box, and so she will check her messages regularly. But if you want to leave her a message, or if Bob wants to leave her a message, he has to write a message and then drop it in the box. And then Eve is sitting in the background and has no idea what is going on because there's no message that she can clearly see. It's all hidden inside this box. And this is the birthplace of public key cryptography. And so, more formally, what we say is that now Alice has provided a public key. She said, use this key and use this method to share a message with me. And that's the idea of the box. Okay, so it's posted in a public place for everybody to see. They can all get to it. They can look at the box, see how secure it is, and then to exchange a message, though, you have to put it in the box, which is to say, encrypt it, and then leave it in a public place for me to access it. And then when I'm ready, I can use my private key. So this little key here is her private key that she has the only copy to, and then she can use this as sort of a trap door to get into the box and access all the messages and also understand all of them. Okay. Meanwhile, Eve is observing this and has no idea what is going on. Okay, so now if we think about this mathematically, we're going to be given a key space K, a message space M, ciphertext space C, and what the key space is going to consist of, every time we choose a key, we're actually choosing two keys. We're choosing a public key that Alice shares with the world, and then she also chooses a private key. Okay, and then what the private, and then in terms of encryption and decryption, the encryption should be something using the public key. Okay, and so that is to say, we're taking a message that we create and then creating a ciphertext from that using the private key. Or sorry, public key. My bad. Okay, and then so the encrypted message is made, we drop it off, we give it to Alice, and it could have been intercepted along the way. We don't really care, because in order to decrypt it, what you need to use is the private key. And so this is going to take the ciphertext, oops, a little big, and give you the original message back. Okay, and so, oops, it should be K private. All right, and so now this scheme, we want to think about, is this going to be a successful crypto system? And well, we haven't established so I'm thinking like the 1, 2, 3, and 4. Okay. So in terms of ease of, encrypting and decrypting, I mean, theoretically, if this is all mathematics, 1 and 2 should be relatively easy to do, right? The encryption process would be made public, and then and actually, this is kind of how banks operate today. Like if you're sending money between banks, or if you're getting paid by an employer, the bank puts out their public key and says, okay, well, if you want to send us any information, you have to use this public key and encrypt it. Great, using our encryption standards, and then they receive it, and then they can decrypt it using a similar algorithm and their private key. So that those 1 and 2 should be relatively straightforward. Again, assuming we get the mathematics all laid out. In terms of 3, so if it's intercepted, is it easily interpreted without the key? And this one is going to say no, which is a good thing. So that one is going to be a success. Now, the only question is, if we receive many plain text and cipher text alongside each other, so that is to say, like Bob, we intercept what Bob originally sends as well as the ciphertext, how easily are the keys found out to be able to interpret any ciphertext? This is going to be relatively hard. But I'm also going to add some question marks because of technology, right? Technology can make these things a lot quicker. So maybe it's bulletproof, maybe it's not. So this is kind of where this idea of asymmetry comes in as well. So the fact that Alice has much more information, so Alice has a private key in addition to the public key. Bob only has the public key. And so this type of crypto system is where we're going to lead into next in chapters 2 and 3. Chapter 2, we have to do a little bit more math before we can return to the cryptography. But apart from that, public key cryptography is now kind of today's standard. So anything that you come across in Cipher or in cryptography nowadays involves public key cryptography.